let's start with the paper. So it is a modeling approach for enhanced marketing expansion and digital marketing in B2B space. So as I told you, it's a kind of recommendation problem. Let's look at the agenda we'll be going forward with. Yeah. So first we go to business problem, then we'll discuss the data set, then architecture, and then other aspects, technical aspects that we did, like how to construct some initial set of users for recommendation, how we calculate distance metric and find similar users, and how we generate recommendation and scoring. Finally, we talk about experiments. Now, coming to business problem, why we are trying to solve this? So given the increasing privacy concerns, as we know, first party cookies, currently users are not allowing us to track, and how we can track their activity and target them. It's not possible in this near scenario. So how we can target users in abundance of the cookies? We kind of used anonymized PI data. PI is personal identifier information data, basically from the first party collection methods. So we have multiple vendors from which we collect data. We use that data to create some seed set of users, or then finding some similar set of users out of it, so that we can basically upload the list of data, like say hashed emails, hashed phone numbers, and all those things on multiple platforms like Facebook and LinkedIn and others. Now, other novelty of our paper is we have the model which is kind of generic, so it serves on multiple platforms, like kind of multiple platform lookalike problem. Here we have some set of features like social and economic. So let's say LinkedIn supports to target users on job titles and industries. Facebook as a platform targets help us to target users based on social features like demographics, behavior, and skills, interests. But there is no generic model which supports both, right? So we kind of tried to solve this problem, basically taking all the features into account, so that if we can create users based on other set of features which are supported on other platforms on a different platform, or like Facebook features, we can use Facebook features to create users to target on LinkedIn and vice versa. On the other end, when we get the initial set of users from the client, they are usually sparse and noisy. So other problem which we try to solve is how to create those users, or basically do some kind of imputation over there. Now I told you about the data set with the features which we are trying to support. Other thing is I will talk about the architecture. So architecture, first thing, we have some kind of seed set creation pipeline. How we created seed set initial set of users which are ground truth data given by the client, or we can have it in a form of ICP, basically ideal customer profile. So basically we can get some kind of job titles which have reacted positively over some campaign or some industries and other things. So how we impute other features, basically other values out of it. So we create some kind of seed set creation pipeline. Then we use that seed set to create our multi-graph. So our multi-graph is something kind of graph in which you give a set of users, it will recommend a k set of users, basically k nearest graph or something. So we have features of multiple types. We have categorical features, we have high cardinal features. So categorical features include job title, job role, job function, work industries, which can take a category, basically a single value per user. And we have some set of users which are high cardinalities in interest, skills. So one user can have multiple skills and multiple interests. How we can calculate some kind of similar users based on that? That's also kind of challenging problem for us. So yeah. So as I told you, we have created I will talk about all of this in future slides. So how we created seed set is basically we have some set of industries. We know if the data is missing, we have to map it to a fixed list which cannot change. So we get some kind of fixed list of industries or job titles from LinkedIn, and we try to map our seed set to that using BERT model and MIL-LSH, basically some kind of similarity measures algorithms. How we created multigraph and why we use multigraph is a big thing. So our goal was to track precision and timeliness. So in normal lookalike models, if we want to generate recommendations, the data scale is very high, let's say 100 million, 500 million, 1 billion. So how we can achieve that process very fast. So that's a timeliness problem. So we use basically some kind of Spark system over there, which gives a very low latency, something around 500 recommendations per second, which is kind of the state of the art. And in precision also, we use some kind of algorithm to build graph, which is HNSW, hierarchy and navigable small world graph. It's kind of graph building algorithm, but the time complexity is little less than KNN graph, which is the state of art previously. So in multi-graph, we know there's a user, we want to buy similar users, we are creating graph between them based on the multiple features. So suppose one client come and says ki, I want this graph with a single feature and want other graphs, or basically want other users with in a single feature, or like other users with same skills, other users with same interests. So we created multiple graphs for that. And since it's offline, so it is very fast to retrieve the users at runtime. Now, we use some kind of metric to calculate distance between the graph edges, or basically users. It's called a Hellinger distance. It's something like we want to create similarity between two users in a feature. So how other features are affecting those that feature of two users. We use that kind of distance metric in that. Now, we are using multiple features for calculating this distance metric as work role, job function, job seniority, and other dimensions. Now, for industries, as it's kind of categorical also, so we use the same distance metric, Hellinger distance, but we use some kind of Jacquard similarity, something like what are the parent industries of those industries. So how many common parent industries are there? Then created some kind of score over there. Then we use this Hellinger distance in that score to calculate some kind of weighted similarity score for industries. Now for skills and interests, since it's a high dimensional feature, each user can have multiple skills like 50, 60 skills. So we can create embedding, it is fine. We can create embedding for each skill, each interest. So that will be a matrix for user like 50 cross K matrix, K is the dimension of the embedding. So we basically converted that matrix into a single vector using optics, which is kind of clustering algorithm, and then fed it to our multigraph for distance calculation. Now how we generate recommendations and how we score them. So our hypothesis was something like scoring of the candidate users are dependent on the seed set. So how similar the candidate user feature values are with respect to seed set. What is the information value which we are getting from the seed set? If suppose there are some set of candidate users which are highly similar in the seed set users, then and their feature values are also same, we say they are basically getting high information out of it. So we score them higher. So we calculate some kind of feature importance out of it and score them and rank them. Now, coming to experiments, so how we experimented is we created a seed set. We divided our seed set, basically initial set of users which responded positively, into multiple parts, let's say n parts. For each part, we fed it to our multigraph, trying to predict the candidate users and see how many candidate users are in n-1 parts. So that's called precision metric. Then we did for all the n parts, basically all the nth seed sets that we divided in, and we calculate some kind of mean precision value. So it was coming really good with respect to state of the art. We did it for, I guess, 2 clients in the POC, and we are doing it right now also. We are running A/B testing out of it. So it was coming really good when we are predicting 200 to 400 users, predicted users. It was coming around 0.85 to 0.9, which is beating the benchmark, I guess, which I saw for other algorithm for LinkedIn and Google. Now, yeah, since our model is working perfectly fine for us, there are still some improvements, but it is working good. So coming to conclusion, the study introduces data-centric approach to B2B lookalike modeling for identifying new customers. Since our domain is B2B, but this model can be expanded to other domains also. Let's say healthcare, finance. If we have some set of users, some set of features which I told you about, like high cardinal or any category of features, we can expand it to other domains also. Addressing job skills, targeting limitations that I told you about, that some platforms support some features, other platforms support other features. Then how can we create a generic model out of it which take all the features into account and do it the same thing for all the platforms. And precision improvement is also there, which is around 0.8 to 0.9 for our 2 clients. I did for other clients also. It was coming really good. Computational efficiency is also there. Basically, I had to, a very low latency model. It's something like 500 queries per second, so which is very good, which plays a very good part for us. And scalability is really good because we fed like 200 million users, 300 million users, and the results are coming pretty fast in the real world experiments with large data set. Yeah, so that's all. Thanks, guys.